Our last shuffle for today is also a judicious transpose, but this time the stacking will be pile 1 on top of pile 3, pile 2 on top of pile 4. Now that's the same as the previous shuffle, but this time we'll stack the right pile on top of the left. And it gives, as we can see here, a very different shuffle. Because if you remember, the previous shuffle was a product of transpositions, 2 cycles. And I should point that out, that the previous shuffle, shuffle 23, has order 2. So if you perform that shuffle twice, you reset the packet to its original order. This one has order 4. So you would have to perform this shuffle 4 times to reset the packet to its original order. Okay, so let's go ahead and prove that this is the cycle notation for this permutation. So we'll begin with our ordered packet and we'll perform our shuffle. So the transpose, it always begins with dealing 1, 2, that, 1, 2, 1, 2, 1, 2. Now the stacking is going to be pile 1 on top of pile 3. We can think of that as kind of a leapfrog stacking. Pile 2 on top of pile 4, also a leapfrog action. But this time, in contrast to shuffle 23, the previous shuffle, we're going to stack the right pile on top of the left. So what is the new ordering that results from that? Well, let's take a look. We get 4, 3, 8, 7, 2, 1, 6, 5. So in Cauchy's 2-line notation, we obtain the following. The top row, of course, consists of just 1 through 8, and the bottom row is this new ordering here, 4, 3, 8, 7, 2, 1, 6, 5. We can convert this to cycle notation as follows. 1 goes to 4, so I have an arrow from 1 to 4. 4 goes to 7, so I have an arrow from 4 to 7. 7 goes to 6, so 7 goes to 6. And then 6 returns back to 1. So that completes this cycle. And in particular, it's a 4 cycle. What about the other 4 values? What happens to them? Well, 2 goes to 3, so I have an arrow from 2 to 3. 3 goes to 8, so there we go. 8 goes to 5, so an arrow from 8 to 5. And then 5 cycles back around to 2. So that completes a second 4 cycle. And that accounts for all of the position values of these cards. If we color code the cycle notation of our permutation, we obtain the following. Recall that the digits are color coded black if they are 1, 4, 6, 7, and the position values 2, 3, 5, 8 are color coded red. So we see here that inversion does not occur. Black 1 goes to black 4, which goes to black 7, which goes to black 6, which wraps around to black 1. So, quote, the black values stay within their respective set. Red 2 goes to red 3, which goes to red 8, which goes to red 5, which wraps around to red 2. So the cards in position values 2, 3, 5, 8 stay within those 4 position values. And so we see that the following has occurred. Each value gets sent to a value of the same color. And when that happens, inversion does not occur. Instead, we say that there's been a preservation of these sets of position values. Okay, so to see that clearly, the 4 cards that began in positions 1, 4, 6, 7 stay somewhere in that set of position values 1, 4, 6, 7. Similarly, for a complement, the cards that originally began in positions 2, 3, 5, 8 will stay somewhere within that set of position values 2, 3, 5, 8. So we're looking at this outcome right here. So applying this shuffle to our Bessey sequence 1, 0, 0, 1, 0, 1, 1, 0, we should expect to get back this same sequence form. So let's go ahead and just perform that shuffle one more time. So we go 1, 2, 1, 2, 1, 2, and then 1, 2. Now we're stacking the first pile on top of the third, the second pile on top of the fourth, kind of a leapfrog stacking, and then the right pile here gets stacked on top of the left pile. So we should expect to get back 1, 0, 0, 1, 0, 1, 1, 0. Now it's very important to realize that even though we got the same sequence form back, it doesn't mean that the cards have not moved around. In fact, we know that all of them have moved around. There is not a single card here that has been returned to its original location before we performed the shuffle that we just did. Why is that? Because as we can see in our cycle notation of this permutation, we don't have any fixed points. Every single value gets moved to a different position than the one in which it started. And so why don't we go ahead, I'm going to go ahead and just set this down. And then I'm going to also put down the sequence that we just got earlier that led to the cycle notation up above for our permutation. Okay, I just want to make clear what has happened here. So going all the way back to the introductory video in this series devoted to Bessey shuffle diagrams, remember, how do we interpret this? So we have a 1 going to a 4. What does that mean? That means first place is now going to what was in the fourth position. Is that true here? Has the first position been replaced by what was in the fourth position? It most certainly has, because we began with the order packet 1 through 8. Okay, moving on. 4 being sent to 7. What does that mean? That means fourth place has now been assigned to what was originally in 7th position. And that is the case. What about 7 here? The 7th place, after our shuffle, has been assigned to what was originally in the 6th position. And finally, 6th place goes to 1, which means 6th place goes to what was originally in position 1. And we see that that's the case here. And then we have a similar interpretation for the second 4 cycle. So let's apply it to the 0s and 1s. So let's go back to 4. We know that first place in this sequence, remember, when the cards are facing down, this card is the top one, the first one. Okay, so the new first place is being assigned to the card that was originally in the 4th position. Well, what does that tell us here? We've performed the shuffle, this very shuffle. So what that means then is what was in the 4th position now gets moved to first place. Okay, so if you undo the shuffle, if you go back before that shuffle was performed, the precise card that was right here is now at the top of the packet. Similarly, 4th place now is being assigned to what was originally in the 7th position right here. So what started out here has been moved to this position right here. In other words, 4th place. And maybe to do one more, 7th position. After that shuffle's done, 7th position now has gone to the card that was originally in the 6th position. So if you go back in time, what was in this position has been moved to 7th place. Okay? And then I guess just to finish, 6th place here, after the shuffle is completed, goes to the card that was originally in the 1st position. So before the shuffle took place, that first 1 at the top of the packet of 8 cards has now been moved to 6th place. So I know that's a lot to take in, but it's really the only way to understand clearly the movement of these cards. And so I encourage you, if you watch the first video, the introductory video in this series, it goes through and gives an analogy using a special packet of cards to explain the true meaning and a helpful interpretation of permutations and how to read permutation notation. Okay, and finally, let's take a look at the shuffle diagram for this final shuffle in our video today. So here we have a product of 2 4 cycles. There they are. Over here we've indicated that inversion has not occurred, and we know that from down here. Remember, black value positions get assigned to other black value positions, and red value positions get assigned to other red value positions. Now the shuffle diagram looks like this. So 1 goes to 4, so you have to focus on here. 1 goes to 4, 4 goes to 7, 7 goes to 6, and then 6 goes back to 1. Okay, so 1 goes down here to 4, 4 goes up to 7, 7 goes down to 6, 6 goes way over here to 1, and that completes that 4 cycle. We also say that the values 1, 4, 6, 7 are members of the same orbit. In a similar fashion, if we begin at 2, we see here that 2 goes to 3, 3 goes to 8, 8 goes to 5, and then 5 wraps around to 2. So 2 goes to 3, 3 goes up here to 8, 8 goes straight down to 5, and then 5 comes up here to 2, completing that second 4 cycle. And that also constitutes an orbit. Note that down at the bottom here, we indicate that this particular shuffle is the inverse of shuffle 26, which will be coming up in our next video. So this shuffle will undo the effect of shuffle 26, as we will see. Finally, let's show an application of all of this.